Okay, this is a problem in rotation, chapter 7, circular motion. And in this case, we have a train that is traveling a certain distance down the tracks. And what we know is that it has an acceleration of 1.7 meters per second. It tells us that drive wheel has a diameter of 1.20 meters, and the initial angular velocity of the wheel is 160 RPM. So what it wants us to do in this problem is three things. The first thing, it wants us to find the RPM of the train's drive wheel at 500 meter mark. We know what it is here at the 0 mark, x equals 0. We know that it is 160 RPM. But we need to find out what it's here. Part B, we want to find out how long it takes the train to go from x equals 0 to x equals 500 meters. And then part C is we want to know how many revolutions does the train's drive wheel make during that displacement. Okay, so let's get started. First thing we're going to ask, find the train's wheel's final velocity. Okay, so to do this, the first thing we should do is that we cannot work in angular velocity in revolutions per minute. We need to change that to rads per second, okay? So let's do that. We have 160 revolutions per minute. And we're going to do our conversion. 2 pi rad is equal to 1 revolution. That'll get rid of the revolution. And then times 1 minute times 60 seconds. Okay, so the minutes will cancel out, and the revolutions will cancel out, and we get an answer of 16.8 rad per second. Okay, so that's a good start. So now we need to do a couple more things. We do a couple more conversions, so it makes it easier to do the rest of the problem. We are given the displacement, we're given the acceleration in meters per second squared, but let's take these two, acceleration and displacement, and let's convert those. Okay, so the first one is the 500 meter displacement. Okay, so we're going to use this equation. And we're just going to solve for delta theta. Okay, what is delta S? Well, delta S is 500 meters. And R is, well, we're told that the wheel is 1.2 meters in diameter. R is just 0.6 meters. And this gives us 833 rad. Okay, 833 rad. What about the acceleration? Well, we're told the acceleration is 1.7 meters per second squared. Acceleration for the conversion is equal to alpha times r. We're going to solve for alpha. Alpha equals acceleration divided by r, 1.7 meters per second squared divided by 0.6, and we get an acceleration of 2.8, the angular acceleration of 2.83 rad per second squared. Okay, so now we're ready. So how we're going to solve this problem? Well, it wants us to find the train's final RPM when it reaches the 500 meters, okay? And so we have an equation that's very similar to one that we learned in kinematics in linear, one-dimensional. And so that is going to be this equation right here, omega minus omega naught, both squared, equals 2 times the angular acceleration times the displacement. This is angular displacement. So that's the equation we need to use, because we know what delta theta is, we know what alpha is, and we know what the initial angular velocity is. We need to find the final. So let's do that. This will be the final angular velocity is going to be equal to the square root of 2 times alpha, our angular displacement, plus omega naught, the initial angular velocity, squared. Okay, so now let's plug everything in. Omega f is equal to 2 times 2.83 rad per second squared, 833 rad. Let's put some brackets around here, plus our 16.8, that's our initial angular velocity, omega naught. And this is all squared, and then all this is under the radical. And so now we can just solve the problem. So when we solve it, use our calculators, 70.1 rad per second. So this is our final angular velocity of the drive wheel when we reach the 500 meters. So, but we need to answer this in revolutions per minute, RPM. Okay, so we have to do a conversion. 70.1 rad per second. And we need to take and get rid of the rad. So downstairs we'll put 2 pi rad. This will cancel out the rads. And up here we will put 1 revolution. And this is, we're going to do the time part now, which is 60 seconds is in 1 minute. Okay, and this comes out to approximately 675 RPM. So we've answered part A. Okay, what about part B? Part B wants us to find the time it takes for the train to move the 500 meters, okay? So in this case, we can use this equation, which would be the easiest one to use. We know alpha, we know the initial angular velocity and the final angular velocity, so we just need to solve for t. So t is going to be equal to omega minus omega naught divided by alpha. Now earlier we converted alpha, so let me just write this down. Alpha came out to 2.83 rad per second squared. So let's solve this problem now. We have, for omega final, we have 70.1 minus our initial was 16.8. These are rad per second. These are our difference between our omegas, divided by the acceleration of 2.83 rad per second squared. Okay, so this is our time, and this is going to give us 19.1 seconds. So this is the answer to part B. So that's how long it takes the train to displace the 500 meters. And at the beginning, it has a RPM of 160 RPM. So 160 RPM at the beginning of the 500 meters. And at the end, it has 675 RPMs the drive wheel is rotating at. Okay, and so let's do part C now. Part C wants to know how many revolutions during the 500 meters that drive wheel makes. Okay, so we're talking about delta theta is equal to 833 rad. And we figured this out in part 1. Now we just need to convert this to revolutions. This would be the answer if you were looking for just rad, but we want RPM, so we have to convert. So this is times 1 revolution is equal to 2 pi rad. And so this comes out to 133 revolutions. So from where the train starts at this point, moves here, we have 500 meters it's moved. Over here is 0 meters. Okay, at the initial we have 160 RPM. We figured out there was 675 RPM. It had a angular acceleration of 2.83 rad per second squared during that, and then it also took 19.1 seconds for the train to move that distance. And so those are the final answers to this question.